if we can start. Thank you for joining this session of Polycon UK webinar. And today we have Alessandra Casella from Columbia presenting a paper, 2 lab experiments on alternative voting rules, cumulative voting and liquid democracy. After today's presentation, we'll take a break for a few weeks and we will meet again at our next event on the 16th of May, when the talk is by Erika De Serrano from Kellogg. The format of the seminar is as follows. We have 1 hour presentation, the official part. We usually reserve a few minutes towards the end for discussion and questions. We request all attendees to keep your microphones muted, but please ask questions in the chat. And if there's something pertinent, please unmute yourself and ask Alessandra directly. After the Q&A sessions, after the official part of the talk, at the top of the hour, we'll finish the recording and we'll stay for a few more minutes to chat informally. If you want, please stay and we can talk more. All right, Alessandra, thank you for joining us today, and the mic is yours.
Thank you very much, Max. I don't know if you saw the poster for this lecture, but I was very proud of it, and it's a Pollock, which indeed conveys, I think, quite appropriately that this is going to be a messy talk. I hope you'll find it beautiful, but it will be messy. And part of the reason it's messy is because I was a bit overambitious and thought I would try to talk about 2 different papers. And in fact, one of the papers has 2 experiments. So we're talking about 3 experiments. So most probably I will not succeed. But there is also one specific reason why I wanted to combine the 2 papers. And it's also related to the very large number of authors that you see on this slide. These 2 papers are the result of a research class that I set up at Columbia. And I want to talk about it because I'm very proud of it. And there aren't that many things of this type that I'm happy with. And the idea was to take a second-year PhD students and myself and start on a project from scratch. So we did everything together from the very beginning. We are absolutely co-authors. The ideas are common to all of us. And the reason I'm talking about it is that I hope other schools will adopt it as well. I think that is something that is really missing in our training of PhD students, this difficult step into research when the students are very young. So the 2 papers are, one is an experiment on cumulative voting that is joined with Jeffrey Guo and Michelle Jiang. And the second paper is on liquid democracy, and that is joined with Joe Campbell, Lucas De Lara, Victoria Mooers, and Dilip Ravindran. So I can tell you more about all of them, but that will take a lot of time. So let me go into into the talk. So let me begin with liquid democracy. And as I said, there should be 2 experiments, but the second experiment is not run yet. So it's 1 experiment and a half. What is liquid democracy? Liquid democracy is a form of voting that has been very much touted, pushed by the tech community and by pirate parties or alternative political parties in Europe. The voting happens online. And this is why I thought we would start with, as a motivation, with this citation from Martin Schubeck in 1970, who says, some sort of computerized participation by large numbers of the public in policymaking is in the cards in the next 10 to 20 years. It may be that we will be able to turn this new technology to the improvement and defense of democratic institutions. I hope so. However, it is by no means evident that this will be the result. So this is really the question, whether the tech community is designing rules of political engagement of decision-making that may improve democracy. And this is very much in the air. So I can hardly believe it, but in the last week, I received 3 different messages from people who were asking me about liquid democracy. And this was, and they didn't even know that I was going to give a talk about it now. So it's really something we should be thinking about. In the simplest form, liquid democracy simply means that each decision is subject to a referendum, but voters can delegate their vote. And the delegation is transitive. So I can give my vote to Max, and Max give it to someone else, etc. The objective, at least one of the objectives, the one that you hear about most, is to improve information aggregation. So for each decision, you want to increase the voting weight of the experts. We want to delegate the vote to the experts, but we don't want to create a group of entitled representatives and politicians who are asked to make decisions on many different themes, not all of which can be something they're competent about. So for each issue, I can choose the expert that I want. People, as often with alternative voting rule, trace it back to Lewis Carroll and this book in 1884. It was proposed in a form very similar to the one that we will discuss by James Miller in '69. There was an immediate response by Shubik, and you heard the quote. As I said, it has been used, in fact, by pirate parties, especially in Germany. So there is a large community in Germany that has been using and talking about it as the golden medium between direct democracy and representative democracy. Better than direct democracy because you can delegate to experts, better than representative democracy because you don't have this group of entitled representatives. As I also said, it's very much one of the dear children of the tech community, in part because you can use blockchain's technology to track delegations, so it's linked to the blockchain world, in part as a form of governance itself in these decentralized autonomous organizations, especially if you are interested in decentralized finance, DeFi, you will find discussions of liquid democracy there. In terms of literature, there isn't all that much yet. Most of it comes from computer science, as you'd expect. And the papers that we listed here typically discuss algorithms on networks. So they are sequential moves described as algorithms that are not strategic. The Armstrong-Van Larsen paper is strategic, but the others are not. In terms of strategic consideration, the type of analysis that we as economists would be more familiar with, to my knowledge, there are 2 papers, one by Dilip, Ravindran 2021, that was part of Dilip's PhD dissertation, and a paper by Martha Dillon and others. And in fact, I believe that these 2 papers are now being combined. So the slide, or if you ask me, I can tell you more about what they do and how they differ. These are theoretical papers. Our approach instead would be experimental. So I will tell you about the experiment we ran. And we start from the very basic question, the point of departure, I think, of voting with delegation, which is, even in a world where you identify the experts correctly, and I actually personally am very worried about that. I'm not at all convinced that we would be able to identify the experts correctly, but suppose you could, even if you can, by delegating, you are reducing aggregate information. So you are losing the richness of independent signals that Condorcet talked about, right? So where does the Condorcet jury theorem sit relative to this theory of delegation? As I said, we will look at an experiment. We built an extremely streamlined model, very, very simple, just focusing on this one question. Therefore, our model will have pure common interest. It will have incomplete information so that equilibria are in pure strategies, and it will look at asymmetric equilibrium. Completely canonical model. And we ask 3 questions. We want to know whether liquid democracy can do better than majority voting. the symmetric setup will be such that majority voting actually works very well. So we want to know whether in that situation it's possible for liquid democracy to do better. Then we want to know whether it does better in the lab beside the theory. And then the third question, which is the one that is most preliminary, we wonder whether there may be something in the lab that can affect the result. So that's what we're going to do. I don't know if you have questions at this type. As Max said, please do ask questions. I like to be interrupted.
I have a question.
Yeah.
So you'll explain what expert means in this Condorcet world.
Yes. Experts will be people who have superior information that is more precise, and you'll see it in a second. Okay. So in fact, you'll see it almost immediately. As I said, the point of departure is a completely canonical common interest model. There are n voters, where n is odd, and there is majority voting. So the decision is taken according to the majority of the vote cast. So there are only two alternatives, little a or little b. There are two states of the world, big A or big B. And we all have the same preference. We all want to match the state. So we want to take decision little a if we are in state A, and little b if we're in state B. We have utility 1 if the choice matches the state, and 0 otherwise. Each of us receives independent signals. These are private signals. They are conditional on the state, and this signal can tell us either A or B. There is a common prior, completely diffuse, pi equal to 1/2, so neither state is more likely ex ante. And the signals have some precision, so we call precision the probability that the sigma says A when the state is A, or B when the state is B. And this probability can depend on the individual, so varies across individual. However, it does not vary across the state. So the probability that I receive signal A when the state is A is equal for me to the probability that I receive signal B when the state is B. And it's bigger than 1/2. All right, so this is really in my mind, this is the canonical Condorcet model, because this is a world in which majority voting does very well. Voting according to the signal is rational, and majority voting aggregates information very well, so that in the limit, the result will be efficient. How about liquid democracy? Now imagine that these n voters are distinguished in two types. There are experts, big E, and there are non-experts. There are K experts and there are M non-experts. The identities, whether you are an expert or not, is known. So again, we abstract from the fact of identifying the experts correctly. All experts receive signals with a certain precision P, and the non-expert instead receives signals with a precision Q of I. Q of I is private information, and it's drawn from some known distribution, and the support of the distribution goes from 0.5 to completely uninformative signal all the way to P. So P is the upper boundary of the distribution from which the non-expert signals are drawn, and it is the common precision of the experts. Okay? Each voter has one vote and will choose whether to delegate the vote or to use it. So you're there, you are Mr. I, you have a certain precision, which you will learn, QI, and you can decide, do I use my vote and how do I cast it? Or do I delegate my vote to one of the experts? In fact, in the model, you can delegate the vote to anyone you want. If you delegate, you specify whether to an expert or to a non-expert, and then the vote is assigned randomly within the group that you mentioned.
Alessandra, there's a question.
Yes.
Hi, Alessandra. Will it matter whether the fact that the uncertainty is on the precision of the non-expert rather than on the precision of the expert?
I don't think so, as long as all the experts have a superior precision to the non-expert. So you can, I mean, I think it could be I want to be able to identify the experts because I don't want to have that complication in addition.
Okay.
I want to make life easy. So yeah, yeah, exactly.
Okay, that makes sense. Okay, thanks.
Okay. All right. So delegation is transitive. However, if a cycle occurs, all the delegations involved are null. Another assumption we want to make is that delegation does not convey information about the signal. So we don't have equilibria where people who receive a certain signal delegate and others do not. If your signal is A, you delegate. If your signal is B, you don't delegate. So one way of solving both of these problems elegantly is to assume as timing that you first learn your precision, then you decide whether or not to delegate, and then only afterwards you receive the signal. I did not specify the timing before. Maybe I should. We have not talked about it yet because in the experiment, we actually don't have this timing. But in the experiment, because of the random matching and the mechanics of the experiment, we don't have to worry about delegation conveying information. So think about this timing if it helps to keep things clear. The signals are not communicated. I mean, this is a common interest problem, so it would be natural to just communicate all the signals and make all information public. This is not happening, as it doesn't happen in standard jury voting analysis, because the application that people have in mind is really to very large elections, where sharing all the signals seems unfeasible and irrealistic. So signals are not communicated, or if you want, the communication is bad. How about the equilibrium? We look at semi-symmetric Bayesian equilibrium in weakly undominated strategies in the standard voting literature approaches. Semi-symmetric and symmetric means that all the experts will choose the same strategy, equilibrium strategy, and all the non-experts will choose the same equilibrium strategy for the non-experts. We have a result, which is for the time being called a theorem. We don't know if it deserves the term of theorem, but it is a general result. And because it applies to such a canonical model and we haven't seen it in the literature, we called it a theorem. And the result is that for any distribution F that is well behaved, for any M number of non-experts and K number of experts finite, there exists an equilibrium with delegation that improves strictly over majority voting.
Alessandra, can I just to make sure, I'm pretty sure I understand, but just to make absolutely sure this is, when you talk about majority voting, you mean that in majority voting, you also have the experts, you all have the same distribution on the queues between experts and non-experts. So everything else is the same, obviously, right? Otherwise.
Yes. So we compare majority voting with the experts, with everything exactly the same, only
you
no
just cannot
delegation.
delegate, basically.
Exactly. That's what we mean by, that's what I mean by majority voting. It's simply that there is no delegation. Everybody has one vote, but the information structure is the same. So one question is whether this theorem is surprising or not. We were not sure that the result held when we started deriving it. So it wasn't obvious to us, but others have told me it was obvious. So let me tell you why it wasn't obvious to us. Well, the first reason is that I said this is really very much of a Condorcet setup. So it's a world where majority voting does very well. And we know that delegation reduces aggregate information. So there is this Condorcet effect, the Condorcet loss. The second reason is that we know that in many cases, the best equilibrium actually requires a symmetric strategy. So there are asymmetric equilibria. And Dilip has characterized this equilibrium, for example, for liquid democracy when there is complete information over the precisions. and you know exactly the number of delegated votes that the experts should receive relative to the non-experts, which will require some non-expert to delegate and not others, which is why you have an asymmetric equilibrium. And we know that that tends to be efficient. In fact, it comes from an older result by Nitzan and Parouche. But we are looking at symmetric equilibria because we are looking at the lab, and we didn't expect asymmetric equilibria with coordination to be realistic in the lab. So we were already moving away from what we thought would be the most efficient equilibrium. So it was another reason why we were not sure the result would hold. And the third reason is that, in fact, the result does not hold if the lower bound of the precision of the non-expert is higher than 0.5, need not hold. So QL is the lower boundary of the precision of the non-experts. You know, this F distribution, F of Q, goes from QL to P. And if QL equal to 0.5 is sufficient to give you the theorem. But if QL is not 0.5, then you might not get the theorem. Of course, it's enough to have any distribution such that you have a small tail at 0.5. So there are some non-experts who are really very badly informed. Anyway, so this is our result. The proof actually comes directly from McLennan. So it's a nice result because it has a very easy proof. We know from McLennan that with pure common interest strategies that maximize expected utility must be an equilibrium. So we know that an equilibrium exists. We can show, and this is the only thing we need to show, that there cannot be an equilibrium. If delegation is allowed, there cannot be an equilibrium where delegation is excluded with probability 1. So majority voting, when delegation is allowed, majority voting without delegation is not an equilibrium. And that's because if everybody else votes, an individual whose precision is close to 0.5, so it's very, very bad information, always wants to delegate. So that means that all equilibria must include a positive probability of delegation. But then there must be an equilibrium that dominates majority voting, because otherwise majority voting would be an equilibrium because of McLennan reasoning that the equilibrium that is best would always be, the set of strategies that lead to the highest expected utility will always be an equilibrium. So there must be an equilibrium that dominates majority voting. And because the environment is symmetric, the result goes through for our world of semi-symmetric equilibria. So this is the first result, which is a theoretical result saying even in this world where majority voting is expected to do well, delegation can do even better.
Can I ask a question?
Yes.
So I'm not sure I understood what K and M are. I remember what they are, but are we talking about any size population of experts and non-experts, including, for example, having one expert and two non-experts? The result would still be true.
Yes. And in fact,
okay.
I'll show you exactly that example in a second. So,
okay.
yeah. Okay. And if there is a follow-up question, ask me after I've showed you the example and then tell me. So just to have a sense of what the equilibrium looks like, consider this case of K equal 1. There is a single expert. Then for any number of non-experts, there is an equilibrium where the experts never delegate and always vote sincerely. And then there exists a unique threshold, Q tilde, which is strictly between 0.5, the lower bound, and the upper bound of the Q distribution, such that non-expert I delegates to the expert, and never to a non-expert, if the precision is below Q tilde and votes according to signal otherwise. This equilibrium strictly improves over majority voting and is ex ante maximal in the class of equilibria that we are considering. So sincere semi-symmetric equilibria with these directions of delegation that I specified. Okay, so this is a very natural equilibrium. It's an equilibrium in cut point strategies. If your precision is low, you will delegate. If your precision is high, you will not.
Alessandra, yeah, I have a question.
Yes.
I think that you're the first one applying McLennan to semi-symmetric equilibria. I mean, everybody else have not condition on known types, which make your proof not trivial at all.
Well, I mean, there is a result. Okay, McLennan has a result about symmetry, right? We have semi-symmetric. So you're right, that it's not fully symmetric, but it's semi-symmetric.
But actually, it's not only that. I mean, the key in the proof that you're using is the fact that the types are known. If the types were not known, yes, McLennan cannot be applied.
Yeah, okay.
So that requires having applied McLennan a couple of times to know. So it's not trivial. Yeah. My point is that whoever argues that, ask them to prove McLennan in semi-symmetric equilibrium, they will have problems.
All right. Okay. So the next time they tell me that this is obvious, I'm going to say, all right, come up here and show me.
Exactly.
Will be done. Will be done. Thank you, Santiago. So let me show the example that we were discussing a second ago. Suppose that you have three individuals. One is an expert, let's call him little k, and I and J are non-experts. Oh, no, there is something, sorry, before I get there, this last line here is important. Equilibrium delegation must be rare. So, you know, intuitively, we know it should be rare because we don't want to lose the richness of information. We are fighting with Condorcet. So on the other side, we know that all this information that is dispersed among the less than precise non-experts is nevertheless valuable. So there cannot be too much delegation. And because we know that this equilibrium improves over majority voting and is ex ante maximal, it must be that in equilibrium, the threshold is indeed low. So only people whose information is very imprecise will delegate. How does it happen? And so this is the example. So consider I is a non-expert, and I has to decide whether to delegate or not. So I's decision will matter only if I disagrees with the expert, because if I agrees with the expert, of course, it doesn't matter. It only matters if J, who is the other non-expert, does not delegate, because there are three people. And so if J delegates, the expert is dictator. And three, it will only matter if J does not agree with K, because if J does not delegate and yet agrees with K, then what I does doesn't matter. So this is equivalent to conditioning on the fact that I disagrees with the expert, but agrees with J. So when you look at the equilibrium condition, you have on one side the expert, on the other side the two non-experts. And this is what gives an extra weight to the information that the non-expert has, even though the precision is low. So in fact, if you use these parameters, and these are the parameters we will use in the experiment, you say that P, which is the precision of the expert, is 0.7, and the distribution of the precision of the non-experts of Q is uniform over 0.5, 0.7, then the threshold is 0.572. 0.572 is not very high here, it's below the mean. This matters, and this is really a point to which I think I'm going to come back throughout the talk, because you have to think about the experiment, I think. Think about the experiment and think about these people who are told, imagine, your precision is 0.6. And there is an expert out there, and we know who he is, it's Santiago, and you know who the expert is, and his precision is 0.7. And we all gain if we make the right decision. Do you want to delegate to Santiago, who has a higher precision? It's very, very difficult. To me, it's completely counterintuitive that anyone would say, no, maybe not. 0.6, I'd rather go to it on my own. And this is, I think, what you'll see in the experiment. This, by the way, this point that I made for n equal 3 is much more general. So with a single expert, the threshold that just indifferent the marginal delegator, non-expert delegator, will condition on at least in fact, on exactly half of all the other non-expert not delegating and voting with her. And so, of course, that gives extra weight, as I said before, to your information. Santiago.
Can I push a little bit on the experiment?
Yes.
So there is this idea that you can think of the swing voters curves as a way of delegating, but if that delegation is not directed, okay, you're giving weight to everybody and
yeah, that's right.
So your result actually holds also if you allow for abstention, right?
We do, and we do in the experiment. That's exactly one of our treatments. So we have two treatments. One is delegation, and one is abstention.
No, but what I mean is having abstention plus delegation at the same time.
Abstention plus delegation.
Because those are two forms of delegation: a directed one, and the other one is like
yes. So we haven't done that.
Because that is, I really would be surprised if they want to delegate instead of abstain.
So I don't know.
I don't know if the worst.
I don't know if Dilip is here or not, but Dilip in his paper, which is somewhat different because he has complete information in the paper he has alone, not with us.
Yeah.
He has complete information, but he has both. He does allow abstention with delegation, and I think his result, if I remember correctly, is that people prefer to delegate, or at least that there is a better equilibrium with delegation.
You know, theoretically there is, but the question is if in the lab
whether they do it. Yes.
Yeah.
I don't know. So let's go to the experiment indeed. These are the parameters as I showed you, as I mentioned before. Precision of 0.7 for the expert, between 0.5 and 0.7 for the non-experts. We fix the number of experts to 1/5 of the size of the group, and we do two treatments with two groups of two different sizes. N equal 5, so 4 non-experts, 1 expert, and N equal 15, where there are 3 experts. And we were interested in what happens when you have competition among the experts. With LD1, the number indexes the number of experts. So LD1 means 1 expert and the small group. And you see that there are 2 equilibria. There is an equilibrium where everybody delegates. So you delegate with probability 1. And the probability that you reach the correct decision, which is equal to the expected utility, is 0.7, which is the precision of the expert. It's only the expert decides. And there is another equilibrium, which is the interior equilibrium with Q tilde equals 0.543. Probability that you delegate is 20%, and you do slightly better than majority voting. This is majority voting. So majority voting does better than a single expert who decides, which we know from Condorcet, and does less well than with liquid democracy, with delegation, with the correct delegation. If you look at what happens when the group is larger, we find a single equilibrium here, and this equilibrium is the interior equilibrium. This is the threshold. The probability of delegating, the ex ante individual frequency of delegation is 16%, so it's even lower. And there is a small gain relative to majority voting, but it's very little. So what is the message from these two tables? The first one is that equilibrium delegation is rare. The probabilities, the frequencies are low. This probability, this frequency falls within, but really the threshold moves very, very little. And the average gains in utility, the available gains, the expected gains in utility are very small relative to majority voting. So this is interesting from the point of view of the experimental design. And, you know, it's really a question, did we choose the right parameters and why did we choose these parameters? I can tell you why we chose these parameters. Of course, if we were to push P very high, so if we make the distance between the precision of the expert and the non-expert much larger, the gains from delegation will increase. So, and vice versa, we can reduce it further if we were to contract the difference. But we didn't want to do that. We wanted to have our parameterization where we could see both directions. We didn't want to push our theory to a corner where, you know, liquid democracy was expected to do so well, we could only find that it did worse, or to do so badly, we could only expect it to do better. So here, we don't really expect to see a difference ex ante between majority voting and liquid and delegation, given our parameters. And we want to see what the lab tells us, given that both directions are ex ante possible, at least in our eyes. Abstention, as was mentioned. Abstention is a simpler route to decreasing the influence of the less informed voters, right? If you don't want the less informed voters to have weight, well, they could just abstain. And it's natural to ask how it compares to liquid democracy. There is a difference, and that's what Santiago said, that abstention increases the weight of all those who vote, not only the experts. So they are not exactly equivalent. There is a paper by McMurray in the Review of Economic Studies that shows that there is an equilibrium with positive abstention that dominates majority voting. The paper is not the model is not identical to ours, but very, very similar. And the result by McMurray carries through to our setup. So in our model, we call MVA1 majority voting with abstention in the small group where there is a single expert. So it's a group of 5 again and a single expert, everything as before. And there are 3 equilibria with abstention. There is an equilibrium where everybody but the expert abstains. There is an equilibrium where no one abstains, and so we are back to majority voting. And then there is the interior equilibrium where non-experts with precision inferior to 0.58 abstain, and all the others do not. And if you look at the larger group with n equal 15 and 3 experts, again, you find the same 3 equilibria. Interestingly, the threshold doesn't change. And as expected, you have an equilibrium that is inferior to majority voting, one that is identical because it is identical, meaning that no one abstains, and the interior equilibrium that is just slightly above. So relative to what we saw before with delegation, the results are very similar, but for the fact that there are more equilibria. So we have these equilibria at the boundaries we didn't have before. And that in the interior equilibrium, the ex-ante probability of abstention is higher than we had for delegation. So this, for example, I was writing that, I wrote here that with in the large group with 15 people, of which 12 non-experts, the expected number of delegators is approximately two, and the expected number of people who abstain with abstention is approximately 5. So you expect higher abstention here. Relative to majority voting, there can be gains, but they remain small. If you look at only the interior equilibria and you compare them, the only really interesting difference, in my opinion, is this higher frequency of abstention relative to delegation. And then here, the impact in the probability of making the right decision is really minute. They're basically equivalent. So let me show you another result related to abstention and delegation, and then I'll take some questions if you have any. Besides finding the equilibrium, a question that I think one wants to ask is how robust are these voting systems to mistakes? So here the horizontal axis is Q tilde, is the threshold. the first panel looks at the small group with n equal 5 and a single expert, and the second panel looks at n equal 15 and 3 experts. Blue is majority voting. The vertical axis is the probability of making the correct decision, the ex ante probability of making the correct decision. Blue is majority voting, orange is liquid democracy, and green is abstention. And you see the equilibrium here with delegation. You see the equilibrium with abstention. But the more interesting finding to me is that the range of possible threshold over which you have gains of a majority voting is larger with abstention. And also the losses relative to majority voting are less. And this is particularly true if you move to the larger group. So if you move to the larger group, you see that abstention does a little bit better than equilibrium delegation. But more than that, you see that the range of thresholds for which abstention has no losses relative to majority voting is almost twice as large as the range of threshold for which that is true under delegation. And when losses come, the losses are lower for abstention than they are for delegation. So there is a sense in which abstention in this model, in this setting, is more robust relative to mistakes. So, any questions?
So can I ask, because so abstention means that you're basically just looking, for example, at the smallest case, you're allocating your vote randomly to somebody else. I mean, in some way, some mixture of expert and non-expert. Whereas when you delegate, you give it to an expert. And
that's right.
So why is it that, I mean, potentially abstention could be superior even in terms of the highest probability that you can get? How does that?
Yes, I agree with you. I don't know the answer. When these are equilibria. So in equilibrium, the people who don't abstain are the people above the threshold, right? And so that seems to matter a lot. Are giving, it's true that you are assigning, in a sense, you can think of approximately assigning your vote randomly to anybody, but you're assigning it to people who are more knowledgeable than you are. And it might be that this dispersion is valuable, yes.
So but maybe what it is that you're endogenously determining the level of expertise that there's going to be when the decision is made. Basically, when you have experts with delegation, you're forcing only those experts to be delegated to. Whereas when you're abstaining, you're basically creating more experts because everybody who's left is in a way an expert.
I think yes.
It would be interesting to see that the average expertise is actually higher. I mean, it could be there are more decision makers. I mean, it could be that the average expertise could be higher under abstention than under delegation.
So
I don't know.
No, average expertise.
It has to be higher than delegation.
I mean,
it is, right?
It is. It depends. Do you weight it by vote or not? If you don't weight it by vote, it certainly is because the threshold is higher, and so we know that. If we weight it by vote, I don't know.
I mean, I mean, including the experts, of course, right? So
yes,
you have
yes,
this 0. Yeah, you have the 0.7.
But the experts are there anyway, right? And so then, in addition to the experts, you have the non-experts who vote, and the non-experts who vote are more precise under abstention because the threshold is pushed.
Yes.
Yeah. So that's certainly true.
Yeah. So that's got to be the explanation in a way that you're controlling with delegation. You're kind of forcing the level of expertise that if you delegate, this is what level of expertise. I mean, not perfectly, because I can choose not to delegate, but given a threshold, you're choosing. You have more control over the level of expertise with abstention in a way, something like that.
I think it's mostly the fact that the threshold is pushed higher.
Yeah.
So that's what does it.
Okay. All right.
Very good.
I have a somewhat related question on the when in the liquid democracy, when you delegate, are the delegated votes spread equally across the experts, or there's different equilibria where you can concentrate more because the signals are independent, right? So if you concentrate all, you're going to lose some of these independent signals.
That's right. And so we just assign them randomly. So we don't assign them equally, but we assign them randomly.
Okay. Yeah, that's how you run it. Okay.
Yeah. So the experiment is basically identical to the theoretical model. We do have a simplification, which is we just prevent experts from delegating, and we prevent experts from abstaining in the treatment with abstention. And under liquid democracy, the non-expert can only delegate to the experts. We run 10 sessions, 150 subjects, random matching across rounds when there are multiple groups. The experiment was run on Zoom, and it was run last summer. And these are the sessions. So we have sessions that are only liquid democracy, where we change the size of the groups, and they play 20 rounds with a smaller group and then 20 rounds with a bigger group. Then we invert the order. We have sessions with only abstentions, and we have session where we mixed abstention and delegation. One of the reasons for changing the treatments in the session, so not running sessions with a single treatment, is also to keep the subjects from getting bored, because these experiments can be really boring, in my opinion. And so you want to diversify a little bit. This is what they have. So results. Participants over-delegate under liquid democracy, and abstention is closer to prediction. So here you have liquid democracy with a smaller group or with a larger group, and here you have abstention with a smaller and larger group. Blue are the data, and gray is the theory. And this is the theoretical frequency of delegation that you should see given the realization of the precisions in the experiment. And it's true for both, and same thing here for abstention. And what you see is what seems to me not surprising, which is that people delegate massively. They delegate 2 to 3 times more than the theory says they should. So the frequency of delegation that the theory predicts are low, but if you look at the realized delegation are very high. As for abstention, on the other hand, the theory predicts a reasonably high frequency of abstention. That's the threshold moving up, that's the Q tilde moving up. And the experimental data show frequency of abstentions that are comparable to what the theory predicts. These results, the excessive delegation, the over-delegation under liquid democracy are very robust. You can disaggregate by session, you can consider only the final round, you can cluster at the session level, and you will continue to find them. And I would say that this is really our main result. I mean, in my eyes, at least, the difficulty of not delegating when you are told that there is somebody else out there that has more precise information and we are solving a common problem. That means that liquid democracy will underperform relative to majority voting because people are delegating too much. And so the richness of the decentralized information is lost. And abstentions result are more ambiguous. So these are frequency of correct group choices. And it's the treatment is in blue. So this is LD1, for example. And this is majority voting. And again, for the others. So you see here that the the data, the experimental data with liquid democracy show a frequency of correct decision that is inferior to the frequency under majority voting, whereas relative to abstention, things are much more comparable. Now, we are still in the middle of analyzing these data, and so everything I'm saying now and in the next few slides is provisional. You might notice a surprising absence of confidence intervals here. There was a question.
Yes, so first of all, there's about 10 minutes left for the whole talk. My question is, obviously, is there maybe a hypothesis here that, there's cost of voting, of actually making a decision that would explain much of that difference? So perceived,
well,
people's perceived.
Yeah. Why? I mean, they are in the lab, right? So in the lab, they have nothing else to do. People, if anything, like to do too much, right? I mean, they don't like to abstain in the lab. You like to do things. But also the two treatments are quite similar, because even in terms of the decision you make, you're going to see a screen that tells you, your signal was green. Do you want to go green, blue, or delegate? Or do you want to go green, blue, or abstain? So it really, to me, seems basically identical in terms of those aspects of the choice. So we're still thinking of how best to calculate standard errors here. It's a bit of a complicated problem because we have repeated choices by the same individuals with groups that change composition. Plus, there is some issue about how exactly we calculate majority voting, because the people who delegate or abstain do not vote. And since we know in the data they don't always follow their signal, although they should, if we were to compute majority voting as simply automatically following the signal, we would make majority voting too good. So we have to compute the probability that they would follow the signal when they vote under majority voting. And the other thing that I think happens is that many decisions are actually very similar. So we need to find the right way to control for all these effects. And one thing we did for now, it's a bootstrapping exercise where we recreated 240 elections with the small groups, which is the number we have. So the number we have in our data, 420 for the large groups. And we generate them by drawing with replacement individual subjects from our subject pool, having the right number of experts and the right number of non-experts. And so we draw 200, we generate 240 elections. That is one data point. And then we do 10,000 simulation of that. And we look at the frequency with which the decisions are correct over these 10,000 simulations. So here you see blue is the density under LD1. So this is liquid democracy, the small group. The share correct is on the horizontal axis, and this is about 65%, 70%. And so blue is liquid democracy and orange is majority voting. So you see that the distribution for majority voting is pushed up relative to liquid democracy. There is a higher frequency of correct decision. And if you look at the CDFs, the cumulative distribution, you have a clear example of stochastic dominance. So this is a measure that shows you how majority voting dominates liquid democracy in our results. If you look at the bigger group, the difference is less pronounced. And you see it in the two distributions that overlap much more. Of course, we are pushing everything up because with the larger group, the probability of correct decision is moving around 0.8. So there is much less room for variation. If you look at abstention, this is the small group. You have almost full overlap. So as I said, the result is ambiguous in terms of welfare properties of majority voting versus abstention. But you see that blue, which is abstention, is beginning to move out a little bit. And when you look at the larger group, you see more of that. So again, you see that whereas before majority voting tended to be on the right-hand side, and so to do better than delegation, with abstention is the opposite. Abstention tend to do better than majority voting. And maybe a better way of saying what I just said is to look at the differences in the frequency of correct choice conditional on disagreeing with majority voting. One of the problems is that too many decisions are the same. So look only at the decisions in which LD or MVA or abstention lead to a different decision relative to majority voting. What is the frequency with which they are correct? The black line is 0. So if you are on this side, on the left of the black line, it means that you are more likely to be wrong than right when you disagree with majority voting. And if you're on the other side, you're more likely to be right than wrong. Blue and green are the delegation cases. Blue is LD1 and green is LD3. Blue is almost completely on the right, on the left-hand side of 0. Orange and red are abstention. And you see that abstention tends to move in the other direction. So maybe we shouldn't put all 4 of them on the same graph, but it is a good summary of what we find. And since I don't have much time, let me tell you about the second experiment that we haven't run yet, but we would like to run. We are very close to running, and I want to hear your reaction to it. The problem is, okay, before I get to that, I keep saying that I find very intuitive that people are over-delegating. I don't know, maybe others don't, but to me, it seems completely spontaneous. It seems to me that exactly the behavior that I would expect people to have. But part of it may be an artifact of the way in which the experiment is run. Somebody comes and tells me, your probability of being correct is 0.6, and Santiago, as I said before, is 0.7. Well, then of course he knows better than me. Of course I delegate. But when I go to vote for real, I usually don't know what's the probability that I'm correct, nor do I know the probability with which the experts are correct, even if I trust that they are more correct than me. So there is a citation from a paper from Margolis, whose title I really like, A Note on Incompetence, where he says, if we don't worry about anybody having a probability of being right below 1/2, why is not decision making completely easy, trivially easy? Why do we ever get anything wrong? Now, if you have a binary choice, you cannot give people signals that are correct with probability less than 1/2 because they can invert the signal. So what you can do is give them signals that are noisy, or even better, a not numerical, not quantifiable measure of the uncertainty attached to their signal. So individuals do not have a precise representation of their and others' precision. That's what I said before about voting. So what we're trying to do is have a perceptual task where the individual perceptual accuracy is the noisy signal. And we are building this on the random dot kinematogram, the RDK, which is a completely classic test in perceptual research and cognitive research. So a number of moving dots are displayed for a short interval, 1 second for us. Some move in a coherent decision, others move at random, and you are asked to guess the coherent decision. When you have 2 directions, they can go either left or they can go right. You have a binary structure. So the objective state of nature will be the coherent direction. And the signal is your individual perception of direction. And people really naturally differ in their perceptual ability. So, for example, I think I'm incredibly bad at this. I don't know how bad I am, but I know I'm really pretty bad. And other people may be really very good, quite good. And that's the way it is. So after you are asked and state whether you think the coherent direction is left or right, then you can vote on it. And you can also decide to delegate. So you can delegate to the experts, which are the 20% of the group with highest performance over the last 40 trials, a number of trials. So let me show you an example of what this thing looks like. So you see the dots very quickly, and then you choose, and then you decide whether to delegate or not. It's very quick. So the decisions are not, contrary to the little video, the decisions are not timed. You have time for your decision, but the video of the dots is really only 1 second. So we did a pilot, and in our pilot we had 15 subjects. So you cannot do bootstrapping with 15 subjects. It doesn't mean anything. It's almost a joke, but we did it anyway because we couldn't resist. And I'll show you to you with the caveat that, as I said, it doesn't mean much. But you see the difference. This is LD1. We did LD1. And you see, this is the result I showed you before. This is delegation blue, majority voting orange. And this is what happens in the pilot. There is much more overlap, although it remains true that you have a tail of good decision with majority voting that you don't have with delegation. These are 1,000 simulations only. There are many things, many reasons why you should not take this seriously at all. One of these is also that the pilot is much more difficult than what we did in the lab. So there is an issue because the range of share correct is different. But beside that, this is the result, and it's intriguing. It's intriguing to me. So it's a way of running voting decisions with ambiguity in a sense. There is uncertainty, but you don't have a precise representation of the uncertainty. You don't have a probabilistic representation of the uncertainty. How does that affect behavior? And so even methodologically and besides liquid democracy, etc., I really wonder about that. Whether the lab, I am a big fan of very precise, very structured lab experiments, but now I'm beginning to have a doubt here, and so I'm reporting it. I don't know how my timing goes, but assuming it's very short, let me just give you some tentative lessons. Remember, we made it really easy here because we identified the experts correctly. So, but even with the expert correctly identified, liquid democracy is dominated by majority voting in our experiment. In experiment 1, experiment 2, we don't know. Abstention emerges as safer and easier. We wonder whether the too precise lab environment is biasing the results. And then finally, it could be that liquid democracy has other objectives. And so there is a lot of work that people could do on liquid democracy, and there are many other questions that can arise, and in fact, also slightly different formulation of liquid democracy. But we probably should have some answers because this might be coming very soon.
Okay, thank you very much. So we are out of time. So let's do the official thanks and Alessandra for a great talk. We are going to stop the recording